In this video, we are going to look at how to draw a Lewis structure, how to determine the shape of a molecule using something called VSEPR theory, and lastly, how to determine whether or not a molecule is polar. So we're going to start out by looking at Lewis structures, and Lewis structures are two-dimensional representations of both the bonds and the lone electron pairs in a molecule. And so here we have several steps to draw a Lewis structure. The first is to determine the total number of valence electrons that exist, not just for one of the atoms, but for all of the atoms in our covalent compound. So we need to look at the periodic table multiple times and add up the total number of valence electrons that all of the atoms have. Then we determine the central atom, meaning which atom is going to go in the middle of our Lewis structure, and then the rest of the atoms will be placed around the central atom. Third, we draw something called the skeletal structure, meaning that we connect all of the atoms together. Fourth, we determine how many electrons are used in our skeletal structure, and then how many electrons we have left to place in our molecule. Next, we give remaining electrons to the outside atoms first. So we don't give them to the center atom until we know how many are left, but we give them to the outside atoms first. And of course, our goal, as always, is to make sure that all atoms have a full octet, or in the case of hydrogen, a duet, meaning 2 electrons. Then we take those leftover electrons and we place them on the central atom. So hopefully we can get both the outer atoms and the central atoms to have 8 electrons. But sometimes, step number 7, if we don't have enough electrons left to give the central atom 8 electrons, this is when we have to introduce multiple bonds. So this is why we wind up with single, double, and triple bonds in our covalent molecules. It's because sometimes we don't have enough electrons to go around, so then atoms have to share more than one pair of electrons. Then once we introduce those double or triple bonds if needed, our final step is just to check our structure and make sure that we have the correct total number of electrons and that every atom in our structure has 8 electrons. So these are the two most common mistakes people make, is they forget to go back and check their structure. So make sure you do this step, and we will look at several examples and we will go through this list of steps together. So in this first example we have CH4, which if we give it its correct name, that would be carbon tetrahydride. So to draw the Lewis structure for this, we're just going to go through our list of steps. So first we need to determine the total number of valence electrons. So we have 2 types of atoms. We have carbon and we have hydrogen. And we have 1 carbon atom and 4 hydrogen atoms. So when I determine how many electrons or how many valence electrons, I'm going to have to multiply by the number of each atom I have. So carbon, I can use my periodic table to find carbon, and it's in group 14, so it has 4 valence electrons. And then hydrogen is over here in group 1, so it only has 1 valence electron. So I have 1 times 4 valence electrons, and then 4 times 1. So I have 4 valence electrons from carbon, and then 4 valence electrons total from the 4 hydrogen atoms. So my total number of valence electrons I get to use is 8. So the most common mistake people make in drawing Lewis structures is having too many electrons in their structure. So it helps to use some counters when you're initially learning to draw Lewis structures to make sure that you have the correct number. So I'm going to use these little pastas here. It doesn't really matter what I use as a counter, but I'm going to count out 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 total electrons to put in my structure, and when I'm making my structure, I can make sure I only use those 8 electrons. So step 2, I need to determine which atom will be in the middle. And the central atom in a Lewis structure is never hydrogen. So even though hydrogen is all the way on the left of the periodic table, it's never going to be the central atom. But in general, when drawing a Lewis structure, the atom in the middle of our structure is going to be whichever atom is further to the left on the periodic table, with the exception of hydrogen. So if I were drawing a Lewis structure with phosphorus and chlorine, then phosphorus would be the central atom because it's further to the left on the periodic table. So, in this structure, hydrogen's never the central atom, so my center atom is going to be carbon. And then my next step is to draw the skeletal structure, which means that I'm going to connect all of the atoms to the center atom using a bond. And a bond is made up of 2 electrons. So if I want to connect my 4 hydrogens, I'm going to place my 4 hydrogens around my carbon, and then hydrogen, so I have 4 hydrogens, and then I need to use 2 electrons to form each bond. So 1 bond, 2 bonds, 3 bonds, and 4 bonds. So my next step, step number 4, is to determine how many electrons are left. And as you can see here, I used up all 8 electrons. So I've already used all 8. I have 0 left. Give the remaining electrons to the outside atoms first. Well, I don't have any electrons left to give. So I'm going to skip down and I'm going to check my structure. I'm going to make sure that the total number of electrons is correct. So I have 2, 4, 6, 8. And that is the number of electrons that I'm supposed to have, so that is correct. And I'm going to make sure every atom has 8 electrons, with the exception of hydrogen, because hydrogen doesn't want an octet, it wants a duet, meaning 2 electrons. So looking at carbon, carbon gets to claim all the electrons that are in the bonds. So it has 2, 4, 6, 8. So carbon has 8 electrons, and then hydrogen also gets to claim all the electrons that are in the bonds that are connected to it. So this hydrogen gets to claim these 2 electrons, and this hydrogen gets to claim these 2 electrons, and this one these 2, and this one these 2. So this hydrogen has 2, which is what hydrogen wants. This hydrogen has 2, this hydrogen has 2, and this hydrogen has 2. So hydrogen is also good because all of the hydrogens have 2 electrons and carbon has 8. So I'm just going to now remove these, and I'm going to replace my every 2 electrons with a line to show that it is a bonded pair of electrons instead of a lone pair. And then this is my final Lewis structure for CH4. So now that I have it correct, I'm going to go ahead and copy it over here onto my answer sheet. CH4. Just like that. My next example is OBr2. So first I'm going to determine my total number of valence electrons. I have 1 oxygen, and I have 2 bromines. From looking at the periodic table, I know that oxygen has 6 valence electrons and bromine has 7 valence electrons. So I have 6 coming from the oxygen and 14 valence electrons coming from the bromine. So my total number of electrons that I get to use in this Lewis structure is 20 electrons. This is my total number. So I'm going to go ahead and count out 20 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Wow, that is a lot of electrons that I have here. So now that I have my 20 electrons, I'm going to determine which atom will be in the middle. And remember, we said that the atom in the middle is going to be whichever one is further to the left. So looking at my periodic table, bromine is here and oxygen's here. So oxygen's further to the left, so that will be my central atom. So oxygen is going to go in the middle, and then my bromines are going to go around it. And to draw my skeletal structure, I know that a bond is made up of 2 electrons, so I'm going to take 4 of my electrons and put them in my structure. So now I need to figure out how many electrons are left. So 20 minus 4, that gives me 16 electrons left. And now I'm going to give those remaining electrons to the outside atoms first. So I'm not going to give any to oxygen right now. I'm going to start by giving bromine electrons until each bromine has 8. So bromine has 2 already through the bond, so I'm going to give it 4, 6, and then 8. So this bromine is now happy with 8 electrons. And then on the other side it has 2, 4, 6, and 8. So I used up 2, 4, 6, 8, 10, 12 more electrons. So I have 4 electrons left, these 4 electrons here that I have left. So what am I going to do with those? Well, leftover electrons should be placed on the central atom. So now I'm going to put these on my center atom. So oxygen already has 2 4 electrons that are in bonds, but it still needs 4 more to be happy, and I have 4 electrons to give to oxygen. So I'm going to give those to oxygen. And I don't have any more electrons left. So I have 0 electrons left. So I did have enough electrons, so I don't need to do number 7, so I'm just going to skip to number 8 and check my structure. So I'm going to replace my bonded electrons. I'm going to pull off these 2 electrons. I'm going to replace it with a line. Pull off these 2 and replace it with a line. And now I'm going to count my total electrons. So I have 2, 4 in my bonds, and then 6, 8, 10, 12, 14, 16, 18, 20 total electrons. And that was the original number that I wanted. Now I'm going to go and make sure every atom has 8 electrons. So bromine has 6 lone pair electrons and 2 bonded electrons. This bromine has 6 lone pair electrons and 2 bonded electrons. So each bromine is happy with 8. And then oxygen has 4 bonded electrons and 4 lone pair electrons. So everybody is happy with 8, which means this is my correct Lewis structure. So I'm going to go ahead and draw this on my paper. Oxygen in the middle, my bromines on the outside, and then I'm going to add my lone pairs. 6, 2, 4, 2, 4, 6. And that is my correct Lewis structure for OBR2. Our last example is SiO2. So first I'm going to determine my total number of valence electrons. So I have silicon, and I have 1 of those, and then I have oxygen, and I have 2 of those. So silicon is in group 14 of the periodic table, so it has 4 valence electrons. And oxygen is in group 16 of the periodic table, so it has 6 valence electrons. So I have 4, so 2 times 6 is 12, so my total number of valence electrons is 16. I'm going to go ahead and count out my 16 electrons. So 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So that is all the electrons that I can use to make my Lewis structure. Next I'm going to determine my central atom, and since silicon is further to the left on the periodic table, I know that silicon is going to be in the middle with the oxygen atoms around it. Then I'm going to go ahead and connect the atoms in my skeletal structure, with each bond being made up of 2 electrons. And since I made 2 bonds, I used up 4 electrons, which means I have 12 remaining electrons. And I'm going to give those remaining electrons to the outside atoms first. So oxygen has 2 electrons already in the bond, so it wants 6 more. So 2, 4, 6. And then the other oxygen also wants 6. So 2, 4, 6. Okay, so now it says give remaining or leftover electrons place on the center atom, but I don't have any leftover electrons. And that's kind of a problem because silicon only has 4 electrons right now, and it wants an octet, meaning 8 electrons. So I don't have enough electrons for every atom to have 8, so I need to introduce multiple bonds, either double or triple bonds. So to do this, I'm going to start moving my electrons from around oxygen, and instead of them being lone pairs on oxygen, I'm going to make them be bonded pairs or shared pairs of electrons. So right now, this oxygen has 3 lone pairs. I'm going to take one of those lone pairs and move it to form another bond between oxygen and silicon. So now oxygen still has 8 because it gets to claim all the electrons that are in the bonds, but silicon has another pair of electrons because it gets to claim these 2 here in the single bond and the 4 electrons that make up the double bond. So now silicon has 6 electrons and it still needs another pair. So I'm not going to take that from oxygen. I'm not going to make this oxygen share more than it has to. So I'm going to take a lone pair off the other oxygen and make another double bond. So now both oxygens have 2 lone pairs and 2 bonded pairs, and silicon has 4 bonded pairs of electrons. So oxygen has 8 electrons, silicon has 8 electrons, and the other oxygen has 8 electrons. So I've kind of already done step 8. I've made sure every atom has 8 electrons. And I'm just going to go ahead back and make sure my total number of electrons is correct. I'm going to go ahead and pull off these 4. I'm going to replace it with 2 lines to show that this is a double bond. And pull off these 4 and replace it with 2 lines to show that this is a double bond. And now I can count my total electrons. I have 2, 4, 6, 8, 10, 12, 14, 16. Now that is indeed what I wanted to start with, so I have drawn this Lewis structure correctly. So last but not least, I'm going to take my Lewis structure, I'm going to put it in picture format on my page. So I have silicon, double bonded to oxygen, double bonded to the other oxygen, and I need 2 lone pairs on each oxygen, which I show as pairs of dots. The next thing we're going to talk about is how we know what shape a molecule is likely to take. And we use something called VSEPR theory. VSEPR standing for valence shell electron pair repulsion. And VSEPR theory allows us to predict the shape of a molecule based on the number of electron density regions. And electron density regions are just areas where an electron is likely to be found. So we consider an electron density region to be either a bond or a lone pair. So if we look at the Lewis structures that we just drew, CH4 would have 4 electron density regions because it has 4 bonds. So this would have 4 electron density regions. OBr2 would also have 4 electron density regions about the central atom because it has 1, 2 bonds, and then 2 lone pairs. So this also has 4 electron density regions. And then silicon dioxide would actually only have 2 because double and triple bonds only count as 1 electron density region. So if we look at silicon, we have 1 double bond here and 1 double bond there. So this is only 2 electron density regions. And when we are looking at the shape a molecule will take, we're looking at the shape about the central atom. Meaning we are looking at the bonds and lone pairs surrounding the central atom. So our central atoms here are carbon, oxygen, and silicon. We're not worried about these lone pairs around the outer atoms, just the lone pairs that touch the central atom. So the point of looking at VSEPR theory is because of molecular polarity, because sharing of electrons in a covalent bond isn't always fair. In fact, it's usually not very fair. The only case where we get true fair sharing or equal sharing of electrons is when we have two of the same atom bonded together. For instance, fluorine and fluorine will bond with each other to form F2. And there are several other atoms that do this, and we call those atoms diatomics, meaning that they always exist in pairs. They never truly exist by themselves. They always come in pairs. We can have one fluorine when it's bonded to something else, but when we just have fluorine, it's diatomic, meaning that they exist in pairs. And the diatomic elements are H, N, O, F, Cl, Br, and I. And so that kind of forms an L shape on the periodic table, which makes it a little easier to remember. But these are something you need to have memorized. So H, N, O, F, Cl, Br, and I. So these ones kind of form an L shape on the periodic table, and then also hydrogen is a diatomic element as well. So, when we have a polar bond, what we really mean by that is that electrons are shared unequally. And then when we have a nonpolar bond, what we mean is that we have equal sharing of electrons, or relatively equal, meaning that there's not too much difference in the amount of electron density that an atom has. And to determine whether a molecule is polar, we look at the bond polarity first. So we look at what the difference in electronegativity is between the bonds, and then we also look at how the molecule is arranged. So if we have polar bonds, we need to look to see if those polar bonds are arranged symmetrically around the central atom or asymmetrically. So the first thing we look at is bond polarity, and bond polarity is due to differences in electronegativity between atoms in a bond. And electronegativity is just the tendency of an atom to attract electrons. So some atoms are better at pulling electrons towards them than others. And generally speaking, more electronegative atoms are seen further to the right on the periodic table. And fluorine is actually the most electronegative atom on the periodic table. But we can get values for electronegativity by looking at a special periodic table that has all of the electronegativity values listed, which you will be allowed to use to complete the activities in this unit and allowed to use on your test. So, high electronegativity means that an atom is more likely to pull electrons towards it than an atom with lower electronegativity. So a polar bond occurs when the difference in electronegativity between two atoms is greater than 0.4. And ionic bonds are just examples of extreme polarity, and usually they have electronegativity differences of like 2.0 or greater. But you can always tell an ionic bond because it will have a metal and a non-metal. So down here, let's look at a couple of examples. So we have carbon and fluorine, and we want to know if that bond is polar. So we can look up the electronegativity values for each of these, and carbon has an electronegativity of 2.55, while fluorine has an electronegativity of 3.98. So if we find the difference between these values, 3.98 minus 2.55, we find that it is much greater than 1. It is 1.0 got to do a little math here, 4.3. So an electronegativity of 1.43, the difference between those two. So that is far greater than 0.4, so this is going to be a polar bond. Next up, we have carbon and phosphorus. So carbon still has an electronegativity of 2.55, and phosphorus has an electronegativity of 2.19. So the difference between these is only 0.36. So that's less than 0.4, which means that we classify this bond as nonpolar. And then finally, we have sodium and fluorine bonded together. So immediately, your senses ought to be tingling, but sodium is a metal. So we know that this bond is going to be ionic, so it's going to be extremely polar. I'm sorry, I know you can't see this. It's going to be extremely polar, but we can check that by looking at the electronegativity of sodium, which is 0.93. versus fluorine, which we already said is 3.98. So the difference between these two is actually 3.05. So this is extremely polar. Extremely polar. And that is, we know that to be true, that it's also an ionic bond. So we get a polar molecule when we have polar bonds that are not symmetrically placed around our central atom. So a polar molecule just means that we have a molecule with uneven distribution of electrons. So in example 1, we have CF4, and I'm just going to draw the Lewis structure here for us. CF4. And of course we have 6 lone pair electrons around each fluorine. So the carbon-fluorine bond we already said is a very, very polar bond. And we show polar bonds by drawing arrows that look like this. We draw an arrow pointing towards the more electronegative atom, and then we show this line at the end. And so we can show that this carbon-fluorine bond is polar and that each of these other ones are polar. But then the question is this molecule polar? And you might say, yes, there's kind of uneven distribution because one fluorine's up and the others are down. And it's not exactly totally even, but in general, since we have arrows pointing in generally opposite directions, this molecular polarity, the bond polarities are going to actually cancel each other out. So this fluorine's pulling electrons up towards it, but these fluorines are pulling electrons towards each of them in turn. So all of that pull kind of cancels out. So we end up with overall a nonpolar molecule. Nonpolar molecule, even though we have polar bonds. Polar bonds, nonpolar molecule. So then let's look at a second example. What if we have CHF3? So instead of 4 fluorines, we've replaced one of the fluorines with hydrogen. So we still have 3 of our fluorines with 6 electrons around each. But then we replace that 4th one with a hydrogen. So this bond between the carbon and the hydrogen, that's not a polar bond. So we're just going to leave it. And then we'll draw our arrows on showing the polarity of our fluorine-carbon bonds. So now we don't have anything to cancel out all these arrows pointing downward. So this molecule is overall going to be a polar molecule, because electrons are drawn in general in this downward direction. So we show the overall polarity of the molecule with one big arrow pointing to the direction that most of the electron density is going. And then our last example is a compound that should be very familiar to you, H2O, which is water. And H2O looks kind of like this. it's actually a bent molecule with the hydrogens kind of pointing downwards, and then our lone pair electrons on top like this. So an oxygen-hydrogen bond is a very polar bond. Polar bond. So we're going to draw arrows on this, and oxygen is the more electronegative atom, so our arrows are going to point towards the oxygen. So if this molecule were straight, if it looked like this, if it were a linear molecule, then you would say, hey look, those arrows cancel each other out. But because this molecule has this bent shape, the electron density is actually all going in general in the same direction, which is sort of upwards. So water is a very polar molecule because of the way that the shape of the molecule is. Because it is a non-symmetrical shape, it results in non-symmetrical electron distribution. So last but not least, I wanted to show you what some of these molecular shapes actually look like using a Phet simulation that gives us bonds and lone pairs and will show us what these shapes look like. So first, let's start by doing something that we've seen before. Let's do CH4. So CH4 has 4 single bonds. So I'm going to add 4 single bonds. As you notice, when I add these bonds, it changes the shape of the molecule. So if I take away one, I have a trigonal planar molecule, but if I add that 4th bond, it makes the molecule something called tetrahedral, and it changes how the electrons arrange themselves. And the reason that molecules behave this way is because electrons all have the same charge. They're all negatively charged. So these shapes result because electrons want to be as far away from each other as possible. So if you notice, when I first put 2 bonds in, these are at a 180-degree angle away from each other, resulting in a linear molecule. But then, for instance, water has 2 lone pairs of electrons, which need to repel those bonded electrons. We end up with a bent shape because of those extra electron density regions around the atom, which makes water a polar molecule with all the electron density going up towards the oxygen atom. And so if you want to, you can come play with this Phet simulation a little bit to get a sense of what molecular shapes look like in space. And if you notice, if I use a triple bond, it still results in the same shape as when I used a single bond. So it doesn't matter what type of bond you have, it still is only one electron density region. So it results in the same shape.